Okay, I guess it's the right time. Let's just start it. Hello, everyone. Welcome to OKX Hackathon Workshop number 1. My name is Dafu, D-A-F-U. I'm the partner at One Piece Labs. We are a Web3 incubator based in Silicon Valley. And for this hackathon, we are honored to work with OKX, Google Cloud, and a lot of different amazing ecosystem partners and community partners. They provide a lot of bounties, credit, judges, and speaker to our hackathon. Thank you for all of that. And for today's topic, this is gonna be our first workshop. This is an introduction to OKX Chain, given by Meng from OKX, and he is the blockchain architect in OKX. I believe he will talk about how to deploy your project on OKX Chain and what OKX Chain can do. Maybe you haven't decided to join this hackathon. However, after this workshop, I hope you can decide to join us because this is a great opportunity to work with and hang out with the VC, layer 1, layer 2 top projects, and also a lot of different hackers. Because our expert is in Asia right now, so today's workshop will be given with video. So I will play the video later. And if you have any questions, feel free to shoot it in the chat box or Q&A box. However, if that is a technical problem, I will say just go into our Discord and type your questions over there because I'm not a coding expert. I wish I could code. If I could code, I would say I would definitely join this hackathon because the prize pool is really huge. I want to win some money. Okay, cool. So right now, let's play this workshop video. Let me share my screen. There you go. Right now, you should be able to see the screen. And this workshop is about 40 minutes long. So let's do it right now.
Hello everyone, I'm Jay. I'm the OKC core developer. Today's video mainly introduces OKC from the following aspects. The first part is the architecture of OKC, which mainly includes the overview of OKC architecture and consensus mechanism. And the second part mainly introduces the functions of OKC. I will introduce EVM, IBC, and Wasm, Gasback.
Oh, sorry, I haven't done this for a while. Can you hear the audio? If you can, please type 1 in the chat box. Meanwhile, let me add the oh, cool. Yeah, you will definitely get a recording after this workshop. Perfect. Yeah, let's keep on this. Sorry for the pausing. Haven't done this for a while.
Hello everyone, I'm Jay. I'm the OKC core developer. Today's video mainly introduces OKC from the following aspects. The first part is the architecture of OKC, which mainly includes the overview of OKC architecture and consensus mechanism. And the second part mainly introduces the functions of OKC. I will introduce EVM, IBC, and Wasm, Gasback, transaction execution in parallel, on-chain government, and so on. Okay, let's start. First, let's look at OKC's entire technical architecture, which relies on tenement at the lowest level. Above is the Cosmos SDK, and tenement mainly contains consensus, which is a consensus similar to BFT, and it has a member pool, a memory pool, as well as peer-to-peer transaction broadcaster, block broadcaster, and consensus message broadcaster. Regarding the transaction pool, we have implemented gas price sorting and support transaction cancellation to be compatible with Ethereum ecosystem. On a further level, the custom SDK provides some basic modules, such as account modules and on-chain government modules. OKC refactored the on-chain governance module and rewrite Cosmos Gap to some of our to meet some of our needs, as well as staking. We have added a lot of proposals for the government, and I will introduce these at last. Speaking of staking, OKC supports depots. That means you can send the Cosmos transactions to delegate your OKT to nodes to earn rewards. Here I want to say that OKC supports two types of transactions, Cosmos transactions and EVM transactions. Of course, you can also complete the delegate OKT through STOKT. You can through this website to delegate your OKT to the node. It actually to interact with contract, not directly interact with nodes. You will get an annual percentage yield reward that's 9.6%. You can connect a wallet through OKX wallet or MetaMask wallet, and you can after you connect a wallet, you can fill the amount of your OKT you want to delegate, and send a EVM transaction as same as you interacting or you send a transaction on Ethereum. Okay, the STOKT is similar to STETH. I think that all is familiar with the STETH. And the next layer is application layer, which we often use to deploy contracts. OKC supports both EVM and WASM, and two virtual machines, and is currently the only chain that supports both EVM and WASM. EVM is familiar with us, so we can deploy contracts. WASM can be used in Rust, but theoretically in C++ or C language. At present, the best support is Rust to write contracts. The top layer is OKC's API layer, which can support Web3 JS to interact with OKC's RPC, because OKC is 100% compatible with EVM RPC. If you want to deploy the WASM contract, you can use WASM JS. And all data will eventually be stored in our database on the right part, including the account as well as storage of contracts and the block of and blocks. This is an overview of the entire OKC architecture. Next, let's introduce the OKC's consensus. I mainly illustrate some features for the consensus. Enchantment actually belongs to BFT consensus, and each block will require all validators to vote for 2 rounds to complete the block or to finish the block. So each block is agreed before going to the next block. Each block is finalized as long as it is agreed. Other chains may have a temporary fork and finally choose a legitimate fork through reorganization. This fork may be detrimental to some security sensitive businesses, and it's necessary to wait for a number of blocks before final confirmation, and there is no need to wait on OKC. We have also made a lot of optimization on consensus to improve our performance, OKC's performance. And one of the optimization is active view change. It does with consensus. Let's talk about the view change. In the logic of consensus or tenement, at every hit there is a validator to be the proposer and create the block. Other validators are waiting and receiving the block in the step of propose, and then sign the block as a valid vote. When valid votes have been collected for more than 2/3, this block is marked as a valid block. There is a timeout mechanism at the step of propose. It means that if a validator doesn't receive the block from proposer within the required time, it will sign a new block as an invalid vote. As a result, it can't collect more than 2/3 valid votes, and this will lead to view change. The view change means the network needs to choose a new block proposer to prevent stopping block production. If the proposer of a hit falls behind or for other reasons, it may not have finished the last block. So it can't make the block of this hit. As a result, other validator can't receive the block, and it will lead to view change. The view change will increase the block time in the between the blocks, and reduce the TPS. Reduce the DPS. We optimize the consensus by adding a consensus message. It is called propose request message. For requesting, it is used to request include a block and a proposal address, original proposal address, and new proposal address. This graph illustrates the working process. Every validator sends the propose request message to the original proposer after they have finished the last block. Request to be the proposer of current hit. The original proposer receives a propose request propose of this hit. It ignores the propose request message and creates a block itself. If the proposer falls behind, it accepts the sender of the first propose request message to be the new proposer and ignores other propose request message of this hit. Then signs the block in the propose request message and broadcasts to other validator a valid vote without timeout, because the propose request message is sent by the first node, which finished the last block. The other validators receive the block, the block with the original proposer's signature, and validate the propose and block, then send a valid vote. So without timeout, it will improve the performance, and it will reduce the view change. So it can improve TPS. The following is a result of OKC optimization. The blue line is the TPS for transfers, and the brown line is the TPS for contract interactions, like deposit, withdrawal, and swap. It should be noted here that the contract interaction TPS is obtained by deploying 5 defined dApps on OKC testnet and stress test. These transactions can be executed in parallel because OKC supports parallel transaction execution. Why deploy 5 dApps? In fact, we are trying to simulate the real sense, because in the real sense, our Meng network, multiple dApps on the chain are running at the same time, and the transactions of different users con different dApps contracts in a block can be executed in parallel. The TPS of the contract interaction can also reach 6,000, and the transfer transaction, the TPS of transaction transfer transaction can reach 6,600. Okay, that's all the part one. I will introduce the OKC functions. The first one is EVM-compatible. OKC is fully EVM-compatible and can interact with OKC through any Ethereum ecological tool like Hardhat, EtherJS, Truffle, and so on. I won't introduce more about this function because there are many document or document about how to interact with EVM-compatible chain, because it is same as you interacting with Ethereum. I introduce the second function of OKC is IBC. OKC supports cross chains with other chains of the Cosmos ecosystem. The Meng network has been connected to many Cosmos logical chains, and the tokens of other chains are crossed to OKC through IBC. Let's talk about the general process of the whole work. That is, a user A sends an IBC cross-chain transfer transaction. For example, transfer atoms from Cosmos to OKC, and the atom is the token of Cosmos Hub, and the Cosmos chain will transfer user A's 5 atoms to the system count on Cosmos Hub. We call this lock. And the second step is Relay. Relay do the pointer stop. Relay does the pointer stop, and Relay listens to IBC transactions from Cosmos to OKC. Relay will send the IBC status and state and proof on the Cosmos chain to OKC. It's step 3. Since the OKC is the same as Cosmos, such as the block header and the state root in it. The block header and state root on the Cosmos chain can be easily verified on OKC because the block structure at the bottom of the Cosmos ecosystem and its entire proof structure are implemented according to the same protocol. In the fourth step, Relay will check the OKC has indeed given user B the same number of mapping tokens and send them to user B on OKC. If you do this, there is also corresponding state as well as proof. Relay then submit the proof to Cosmos. In fifth step, IBC acknowledge is a confirmation transaction. Therefore, it's necessary for Relay to send at least 2 transactions to help a user complete the entire cross-chain transfer. It will not be seen for user. And ERC20 contract will be automatically deployed on OKC for the token. because OKC supports EVM, and the token directly becomes ERC20 token after transfers from other chains to OKC. So your cross-chain token can directly participate with OKC's DApp, which is implemented through Solidity contracts. That's the IBC on OKC. The next is Wasm. It's permissive currently, and you can issue a proposal to apply for deploying Wasm contract. This part you can refer to. Wasm module in the document of OKC, and it is feel very detailed. Okay, I can demo the IBC transfers from OKC to other chains because I have no tokens on other Cosmos chains for the transaction fee. So let's demo a transaction from OKC to other chains. If you want to send a cross-chain transfer token between OKC and other chains, you can use website IBC transfer. The first you need to connect a wallet because then the IBC transfer because the IBC transfer transaction is actually Cosmos transactions. So you need to connect the Kepler wallet. It's a wallet in Cosmos ecosystem. So I connect a wallet first. I open the Kepler wallet. I can choose the OKC mainnet. So I have 0.0 about 0.05 OKT. So I can transfer some OKT to other chains like Osmosis. I need to you can also transfer send cross-chain transfer directly in the Kepler wallet, or you can through this website. In this website is more user friendly. So I choose OKT, and from OKC to Osmosis, and I fill the amount. Okay. The destination address, I need to choose Osmosis, my address on Osmosis. I will introduce some information about the Kepler wallet. We will see two address for OKC. Is my account name, and I have two address for this account name. The two address is the same byte slice in the bottom. The first address is a bench 32 address. It's just a address format. The two address actually is the same byte slice. So I choose Osmosis. This is my Osmosis address. I copy this address. So you can I have 0.05 OKT on Osmosis because this OKT is a token I sent before from OKC to Osmosis. Okay, I paste this address and transfer. You can confirm. Okay, I need to refresh this website. Test Osmosis I fill the point transfer and confirm. Oh, it will pump a window. I need to approve this transaction to finish the cross-chain transfer transaction. I approve this transaction. Okay, I need to. The transaction has been completed. You can view the transaction detail in the Explorer. Okay, the status is success. I will check to in my wallet, in my Capital wallet, osmosis. I need to switch to OKX Midnight. Okay, I have in my address there is less 0.01 OKT that I transferred. Okay, switch to osmosis. Okay, I have received the 0.01 OKT. Okay, that's the demo IBC transfer from OKC to other chains. You can try this the IBC transfer. Use a Capital wallet or this website. Okay, let's come back. The next I will introduce is guessback. The guessback function is a developer dependent function specially launched by OKC in order to encourage developers to deploy and build OKC ecosystem. If deployer registers the contract you deployed to guessback, as long as the contract is called by the other users, part of the gas fee consumed by the transactions will be returned to the developer, so that the developer and OKC can grow together and enjoy the benefits brought by the prosperity of OKC ecosystem. If you are a contract deployer, you can register your contract through this website, guessback website. First you need to connect a wallet, and I will also fill your address, the default address in your wallet, and the second blank is your contract address. The contract address is deployed by the wallet address, and the third blank need to be filled the receiving the benefits address. This address can be different with the wallet address. The last one is the guessback rate. It means a transaction fee is if a transaction fee is 0.05 or 0.2 OKT. A transaction call your contract you deployed. The receiving address will receive 0.01 OKT for the guessback. Currently only support registering contracts deployed by UA address, not support deployed by contract address. It means the second blank can't be the contract address which deployed by another contract address. For more information, you can refer to the document. You can refer to guessback in OKC document. It's here. Guessback module is the more detailed information. Okay. After introduce our guessback function, let's introduce the parallel execution of transactions. Generally in blocks, in blockchains, especially in blockchains such as EVM, transactions are executed serially. Why? Because the state it can access for each transaction is uncertain. Transaction 1 and transaction 2 may access the same state, such as the state transaction written first by transaction 1. A transaction 2 to read the state. If you go to parallel execution, a transaction 2 will depend on the modified state of transaction 1, so it is necessary to execute serially. We analyzed it here. In fact, we found that when multiple dApps are running at the same time, when they don't have this state dependency, these transactions can be parallelized, such as transaction 1 and transaction 4 to access the state of the same dApp. Transaction 2 to access the contract and state of another dApp, and transaction 3 to access the state of the third dApp. So from 1 to 4 from transaction 1 to transaction 4 in this graph generate as 5 based on the very starting state. Transaction 2 also generate as 6 based on the very starting state. Transaction 3 generates intermediate state as 7. So as 5, 6, and as 7 are all intermediate state. There is no conflict between the read-write sites used by S5, S6, and S7. When merging, when there is no conflict, it can be parallel. It can be parallelized. After the parallel execution of these transactions, we can directly get a final state like serial execution. To give a simple example, the right ones are transactions that can be executed in parallel, such as transaction 0, transaction 2, and transaction 3, transaction 4, and transaction 5. These transactions can all be parallelized. Why transactions cannot be parallelized? Because, for example, the transaction 1 and the transaction 0 access the same dApp's contract. They can't be executed in parallel because the state of transaction 1 access may be modified. The state of transaction transaction 1 access may be modified by transaction 0. So you must rely on state after transaction 0 execution. But the state of transaction 0 modification will not be read. They will not be read by the 2, 3, 4, and 5 transaction. So their read-write sites have nothing to do with it. So they can be executed in parallel. So it can be grouped simply according to the from and to of a transaction, from address and to address from our transaction. For example, it is divided into 5 groups of 0, 1, 2, 3, 4. Each group is serial. And the groups are executed in parallel. So this improves the TPS. Look at the follow chart below. Groups are parallel to each other, all based on the initial state, and finally go to merge. Of course, it is also possible that our grouping is inaccurate in extreme cases. It doesn't matter. It is executed in parallel first, and finally there is if there is conflict during the merge, and then re-executed. We go to that's all the for the transaction execution in parallel. We go to government on the OKC, such as modifying the parameters, such as the parameters on the chain of OKC without modifying the code. Only need to send a proposal transaction, and a certain parameter on the chain can be modified after the community votes. For example, like Ethereum, if you want to change a certain parameter, you need to upgrade and send and release a version, and it will need all nodes to upgrade this version. OKC is not needed. For example, the size of your validator site and the gas limit of the transactions can be completed, can be changed through parameter modification proposals. The above is an overall introduction to OKC. Starting with the architecture and block consensus, there are also some performance optimizations. And of course, the code for these performance optimizations is already open sourced. There is also OKC's EVM-compatible function on this basic. We add ABC vaults and parallel execution of transactions. On-chain governments and so on are supported. The above can basically give everyone a global understanding of OKC. Of course, there are some performance optimization details. Because of the time, I will not repeat them here. Well, thank you all. If you have any questions, you can ask them on GitHub or Telegram. We will still very active in community technical support. We will respond to any questions as soon as possible with attitude of growing together with the community. OKC can be better used by everyone. Thank you again for today's introduction.
Okay, thank you, Jay. Thank you, Jay. Even though you are not here, but still, thank you for the efforts of making this video. So hackers, right now you have completed OKX Hackathon Workshop number 1. I hope this workshop have given you enough information about the OKX Chain basics. We have 4 more workshops coming this Sunday, coming Monday, Tuesday, and Thursday, all at the same time, 6 p.m. Please join us then, the same Zoom link. And for those who missed this workshop, we have the recording on the Notion page in our Discord and also in OKX Chain Twitter. Let me also have the Notion page in the chat box. So if you haven't joined the Discord, you can click here in the chat box. And next, that is our Notion page. We have all the detailed information about this hackathon on this website. Cool. So if you have any question, feel free to join this Discord and go to OKX Hackathon channel. And we have tech support over there. You can ask them all different kinds of questions. And I hope after all the workshops, you will be an expert on OKX Chain and you can win some prize from this hackathon. Okay, thank you everyone for joining this workshop. I will see you next time. Bye-bye.